Okay, you're sending a probe from Earth to Saturn. We actually did this. We've done it multiple times. Obviously, the Voyager, was it Voyager 1 or Voyager 2, swept past Saturn and took a bunch of great pictures. And then many years later, we sent a probe called Cassini. And its whole job was to take a whole bunch of observations of Saturn. And then it was just a couple of years ago, we finally ended its life artificially because we were concerned it might crash into one of Saturn's moons that were suspicious may have life, conditions for life. I believe it's Enceladus, if I'm not mistaken. It's like an ice world that could have ocean life underneath it. So anyway, crashed into Saturn's atmosphere, and it took some really cool pictures as it literally was burning up into the atmosphere. It sent back a couple of pictures, like as its last kind of memoriam. So anyway, this is a real thing. We've done this. And if you remember from last time, again, I put out the notes that we used, or the notes that we generated from last week, but I thought I had a better version of them. But anyway, we're going to basically calculate V infinity, and then we're going to calculate V infinity again of the other planet, and then we'll calculate our delta V boost and our delta V retro. And obviously, like all astro things, we want a total delta V in the end, right? That's what we're really looking for. So, all right. Now, I think it might be helpful for me to just set up my picture real quick. All right, here's the sun. Here comes the sun. There's all the rays coming out of it. Okay. And it has its own gravitational constant, mu of the sun, and that's the little symbol for it, the circle with the dot. And then let's see. Let's make Earth orbit. Oh, wow, that's a terrible Earth orbit. Doesn't matter. Here's Earth. And our spacecraft is going to have a parking orbit around that. And Earth itself has what we call a sphere of influence, beyond which its gravity is pretty much negligible. Cool. And then let's, oh man, here. I should have picked a place with more room, but that's okay. All right, why is my, literally it looks like a pencil. Ugh, man, I don't know why. Sometimes my iPad does things I do not understand. I'm still learning. There we go. There's Saturn. And it has some rings and a little hazy atmosphere, right? Saturn, we're going to enter a parking orbit around Saturn. and Saturn itself has a sphere of influence. Sorry, this is not to scale, but it doesn't really matter for the drawing itself. Okay, what we're going to do once we're in our parking orbit around Earth is we're going to do a burn. It's called delta V boost. Let's zoom in way far. So delta V boost occurs there, and as soon as we hit, here actually, let me just draw the whole path. That's going to put us on a trajectory towards Saturn. Then we'll do a second delta V right here. This will be called delta V retro. One more thing of note. Out here, as soon as we exit, like that exact point where we exit the Earth's sphere of influence, we'll be going, we just call this V infinity. And that's specifically V infinity of Earth. Same thing happens when we enter Saturn's sphere of influence. We're going to be going V infinity Saturn. That just happens to be the speed that we need to be going to get captured by Saturn's sphere of influence, which we do want, right? We want our spacecraft to get pulled in by Saturn and not accidentally fly past it. That would be useless. Okay, that's our situation. And what we want to know is total. Actually, here, I'll put it like this. We want to know the delta V total required to get us to Saturn, which consists of that delta V boost plus the delta V retro. Okay, that's where we're going. I'm going to make everything black and stop color coding just to get through the math part. Okay, get out your equation sheets if you don't already have it. We're given this table: Earth data, Saturn data. We're given the gravitational constant for each, the radius of each planet's orbit around the sun, and the radius of the parking orbit around each planet that our little probe will have. So we'll launch from Earth into a parking orbit, do our checkout, and then we'll fire and travel for years in between planets, and then we'll finally do another firing when we get out to Saturn. So that's kind of how that's going to work. All right. So the first thing it asks is, how long will this trip take? And you're like, oh, sorry. There we go. Go like that. Change my iPad a little bit. So whenever someone says how long will, it's asking for time of flight. And as per usual, we always know that period is 2 pi a cubed over mu. But when we have time of flight, we're only ever in an orbit for a half an orbit. Usually that's the assumption we make. So we'll find the center major axis of that transfer orbit, just like usual, over mu. Which mu, though? Well, when we're flying between planets, our little probe basically becomes another mini tiny planet orbiting the sun. Right after we've gotten out of the Earth sphere of influence, we're basically flying high on our own. So that's what we're going to use mu of the sun. Bookkeeping is so important for interplanetary. It's literally where you make all your money here. So, okay, well, let's find what the center major axis is then of the transfer orbit. Well, I can show you, right? There's a distance between the center of the sun out to the center of Saturn, and a distance between the center of the sun out to the center of Earth. I'm going to call this distance, I'm going to call it R sun to Saturn, which is a little h with a cross through it. I'm going to call this distance R sun to Earth. Sun to Saturn, sun to Earth. Okay. And we're given those distances. So here's one, and here's one. So let's plug and chug. Times 10 to the 8. Okay. Plus 1.43 times 10 to the 9th. Cool, over 2. Where'd my calculator go? I forgot. I brought it to work with me. Okay, now I got it. 1.496 E8 plus 1.43E9. 5 by 2. This should be 7.898 times 10 to the 8th kilometers. Now we have all we need to do time of flight, so let's do that. Oh, that should be cubed. There we go. And then mu of the sun is straight off of our equation sheet. It's not in the table. I'm going to write it on the table, though. It's on the equation sheet in the interplanetary section. Wow, that's the worst 2 ever made. That's better. All right. So let's see how long the sucker takes. It's in PS, it's going to come out in seconds. So it's going to be some ungodly massive number of seconds. Times pi. I get that it's 1.914 times 10 to the 8th seconds, which nobody knows what that is off the top of their head. If you do, I applaud you. But if we convert that to days, right, like if we divide by 3,600, that'll give us how many hours? And it's 53,000 hours, which still means almost nothing to me. So if we keep converting that, right, divide by 24, divide by 365.25, maybe that'll give us a number of years that makes sense. Yeah. Oops. There you go. 6.06 years. That's how long it takes to get to Saturn. Wow. We're used to dealing with like minutes and hours. Nah, son. Saturn is so much farther away. In fact, if you look, like 1.496 times 10 to the 8th versus 1.43 times 10 to the 9th, it's almost 10 times farther away from the sun than the Earth is. So I don't know if I told you guys this, but if you were able to put Saturn in a bathtub, it would float. I don't know if you guys knew that, because it's overall its average density is less than water. That's fun. Okay. That's not very fun if you run into me. Okay. Calculate V infinity of Earth. Remember, V infinity is the speed we're going right at the moment we exit the Earth's sphere of influence on our way to Saturn. So it's specific for this path. Right. So like V infinity of Earth is not just some property of Earth. It's specific for the Earth to Saturn path that we have constructed for this problem. So how do we get it? Well, overall, here's what we're looking for. And I'm going to label it like this: V infinity of Earth with a little symbol for Earth, right? And just in case you need a decoder ring, Earth, Saturn. You don't have to know the little symbol like H cross. It beats the heck out of writing the word Saturn each time. Okay, those are the little subscripts. So the equation sheet tells us that it's the absolute value of the velocity of Earth itself going around the sun minus V transfer at Earth. V transfer at Earth is the speed at which we need to go to kick us onto that Saturn insertion orbit, basically, that Saturn travel orbit. So V infinity is not going to be a delta V, but it's sort of that similar math where you're taking the absolute value of two things minus. But what are those two things? Well, the velocity of Earth around the sun is good old square root of mu over r. We assume it's a circle because it is almost exactly a circle. But since we're treating Earth as the satellite around basically another body, we have to use that body, which is the sun, as its mu. And the radius of Earth's orbit is the radius from the sun to the Earth. So the math is easy, but the bookkeeping it requires a fastidious attention to detail, put it that way. So how far out is Earth? Okay, 1.496 times 10 to the 8. Okay, 1.327 E11. 1.496 E8 square root. Whoa, not answer squared. That is not what I want. 29. There we go. 29.783 kilometers per second. That's not. If you're standing on the surface of the sun, you would watch the Earth at a very far distance, flying around at almost 30 kilometers a second. It's hard to even envision how fast that is. It's ridiculously fast. Okay, cool. Now let's see what V transfer at Earth is. You will recognize this equation from the good old days. From the good old days. Put it that way. Back when we used to see each other in class. So it's this mu over r, right, plus epsilon, that whole thing again. Just like a homotransfer, this epsilon is negative mu over 2a. Trick is, it's going to be mu of the sun over a of the transfer orbit, which we found in part A right here. So really, it's kind of the same. And then, of course, the radius we're using, we're specifically right now talking about the Earth going around the sun. So we'll use that sun-Earth radius. And now we shall plug in also, we shall chug to 1.327 times 11. Should be 11. There you go. Minus 1.327 times 10 to the 11. Over 2 times, what was our transfer orbit? Yeah, 7.898 times 10 to the 8. Whew. Okay. Calculating. Whew. Yeah, so we need to get really going here. 40.075 or 76, I guess, kilometers a second. That's our V transfer at Earth. All right, so let's plug both of those back into the V infinity Earth equation. So V infinity Earth, right? Again, I'll rewrite it down here. Velocity of Earth itself minus V transfer at Earth itself. It should be Earth. Let me erase that. Erase. Enhance. Enhance. Okay. Absolute value 29.783 minus 40.076. All right, sweet. Minus 10.293 kilometers per second. That's V infinity at Earth. Okay, so that's the speed we're going to be going at the moment when we exit the Earth's sphere of influence. Just for fun, not just for fun, we have to, but it is fun. We're going to repeat the process for Saturn, and it's going to look exactly the same, just with Saturn's numbers instead of Earth's numbers. So V infinity Saturn, V Saturn itself, minus V. It's terrible. I need to slow down. Attention to detail. V transfer at Saturn. Okay. V Saturn itself. Still going to use mu of the sun because Saturn is also orbiting the sun, but we're going to use that radius of sun to Saturn orbit radius. Let's see, what was that again? 1.43 times 10 to the 9th? Okay. 9.633 kilometers per second. Saturn's not going as fast as I thought it would be, but it is 10 times farther away from the Earth, or from the Sun, as the Earth is. Okay, cool. All right, V transfer at Saturn. So what speed are we going to have to be going to get captured? T at Saturn equals square root of 2 mu. Wow, that is not what I meant. Sorry. Mu of Sun over R Sun that plus epsilon. Epsilon's the same epsilon. No. We used up there. Same one. There we go. Okay. 7.898 times 10 to the 8. Whoo! That's no joke. That is no joke. Not hard, though. You guys have seen all this before. Just a matter of bookkeeping. All right, I get 4.193 kilometers per second for V transfer at Saturn, which means V infinity. Saturn is that absolute value of 9.633 minus 4.193. 440 kilometers per second. All right, let's take a break and just think about what we've done so far. What we've done so far is we figured out how fast we'd be going at the moment we exited the Earth sphere of influence, V infinity Earth, and we found out how fast we'd be going when we entered Saturn's sphere of influence, which is V infinity Saturn. All right, now we get to the real work, if you will, of finding the delta V's. I'm going to ignore part E here because we already did that. Well, we drew a big picture. I guess I could draw a little picture. So let me draw the picture first, and then we can get back to our process. So an Earth-centered picture showing where delta V boost and delta V Earth both occur. Okay, so check it out. There's Earth. Yeah. Here's our parking orbit around Earth. Out here's Earth's sphere of influence. And let's say that's kind of an excerpt of the Earth's orbit around the Sun. So your spacecraft launches from Earth, right? Again, we're not going to ask you to go all the way from launch to Saturn. We're just going to say you're in a parking orbit already. But just for the purpose of telling the story, you'll be in a parking orbit for several orbits, get the probe all checked out, and then it's time to burn. Boom. Delta V boost will occur right here. And that will set you on your way going to Saturn. V infinity occurs right at this point, again, where you leave Earth's sphere of influence. It happens right there. Or, I guess to be even more specific, right at that exact intersection point. So, delta V boost occurs when you're actually in your parking orbit, and V infinity is just a speed you happen to be going at a certain moment in time. It's not an actual thruster firing. So, all right. So back to the math. Delta V boost. Here's what our equation sheet tells us, and it's a little bit vague, so heads up. It says delta V equals absolute value of V park minus V hyperbolic. That's true for delta V boost, and it's true for delta V retro. It's just context sensitive on which planet. So here's what I mean. Delta V boost equals V park. So this is how fast the satellite's going in orbit around Earth, minus V hyperbolic at Earth, which is the speed we're going to have to get up to in order to put us on the Saturn trajectory path, starting from the parking orbit. So here's the math. V park is what we've been doing literally since September. It's the square root of mu of Earth over R park, which we're given. It's up here. So let's see, R park 6778. And if it's like everything else we've done in the course, it'll be around 7 kilometers per second. Yep, 7.669. Oh, whoa. Kilometers per second. Okay, what about V hyperbolic? This is where things get a little bit new and fresh and different, because the rest of this is all Hohmann transfer math that you've seen before, essentially. V hyperbolic at Earth, that's equal to 2 times mu of the planet, in this case Earth, over R park, plus this thing called epsilon infinity. So, okay, this is kind of a review, but like if you remember for like a closed orbit, like a conic section of some kind, well, I mean, I guess they're all conic sections, but a closed conic section will have a specific mechanical energy that's negative. But hyperbolic trajectory, you know, you'll have a positive specific mechanical energy, which is weird, right? And if I, the final review packet has a little table for you to fill out, which helps you remember these things, like what's the semi-major axis of all of these? What's their specific mechanical energy, positive, negative, or 0, or whatever. So, cool. Anyway, epsilon infinity is this new value. And so, like, for example, it's going to vary from Earth to Saturn, but for Earth's version, this equation sheet tells us it's V infinity of that planet squared over 2. And that's what we're going to put in for E infinity. So it's time to plug and chug. This is going to get a little messy as far as space goes. They didn't give us a whole lot of space. That's okay, though. Oh, wow. Even I used the wrong mu here in public math. Oh, I was wrong. Jeez, man. It could happen to anybody. Don't let it happen to you. Okay, V infinity of Earth was all the way up here, and that was, 10.293 squared over 2. Okay. All right, so let's calculate. Times 2, square root of the square answer, 14.952. That's our V hyperbolic. So that means delta V for the whole boost to get us away from Earth and on our way to Saturn is going to be absolute value of park minus hyper. And of course, our Earth orbit from the next problem is protruding. 6. So there we go. Okay. Woo! 7.283 kilometers per second is how much delta V it takes to get on our way to Saturn. What? That's literally as fast as most things in Leo are going, just going. So like you guys learned, just a few kilometers per second of delta V takes a massive tank, but 7 takes literally its own rocket. So that's pretty neat. All right, delta V retro. Again, as a reminder, we're going to have to do this retro burn as soon as we hit our parking orbit around Saturn. And it's going to be the same process. Sorry, I scrolled past it. So delta V retro is going to say, or is going to equal velocity of parking orbit at Saturn minus V hyperbolic at Saturn. Okay, so how fast are we going to be going in our parking orbit around Saturn? Let's see. Mu Saturn over our park Saturn. What was Saturn's mu? 3.7967. Times 10 to the 7th, okay, over our park, which, oh, I should have looked, what, 10 to the 6th kilometers? Okay. That's pretty far out, but then again, Saturn's pretty big. 6, 7, E7 divided by 6.162 kilometers per second. Okay, V hyperbolic, right? We'll just call it V hype. V hype Saturn is 2 times mu of the planet. Wow, why did I write planet? Because the equation sheet said. There we go. Our park Saturn plus, E infinity of Saturn. Oh man, we can do this. .7967 times 10 to the 7th over 1 times 10 to the 6th plus, what was, 5.44, okay. Over 2. All right, let's see what that comes out to be. .7967 E7 divided by 1 E6 minus 5.44 squared divided by 2 times 2, 6.807. Yeah. All right. So our retro boost we'll have to do isn't so bad, actually. Something, but not so bad. Whoa. .645 kilometers per second. That's our retro firing we'll have to do. All right, cool. So again, the holy grail is delta V total. That's what we did all this work to get. Let's see, our boost was, there we go, 7.283, and our retro was 0.645. 7.928. That's what it takes to get from Earth to Saturn and then get captured at Saturn. Ta-da! All right, y'all. That is interplanetary travel. That process is the same whether it's Earth to Ceres, Ceres to Mars. Literally, I mean, it doesn't matter the planetary body. It really doesn't. All that matters is you keep track of your mu's and your r's, and you're pretty much set. So I want to hear I do want to hear any questions you guys have about this, and I'll post this if that would help.
Sir, can I just have you reiterate what it means by delta boost and delta V retro. Like, I don't understand what it means by like retro. Like, why is it different?
Yeah, so the delta V boost is the firing of the rocket engine to get you out of Earth orbit and on your way to Saturn. They have to basically tilt the spacecraft around and fire the rockets the opposite direction when they get to Saturn, or else you'll speed right past it. So that's why they call it a retrograde firing, or retrograde. I'm not sure, but it's retro something firing. You don't have to know that, but it's against your direction of motion to slow you down a little bit so you get captured by that other planet. So really, you just call it delta V1 and delta V2 if you wanted to. But the
Okay,
retro.
thank you. That makes sense.
Okay, good. Okay, cool. All right. Other questions about this? Okay.